So this is my Lab 2 magnetic field of a bar magnet. So just table of contents wise, I'll be going through key ideas and fundamentals, the purpose, results preview, experiment, assumptions, overview, observations, result, coding explanation, the magnitude of the magnetic field, and then the what if questions. So here's just a few of the equations I'm using on the Biot-Savart law. The first equation 1 and 2 are distance dependence equations, and they basically say they help you find the magnetic field of a dipole, and then the distance dependence equation 3 helps you find the magnetic dipole moment. So the purpose of this lab is to measure the distance dependencies of the magnetic field from a small bar magnet and compare it to the on and off axis magnetic fields which are derived from the Biot-Savart law in the first place. So the distance dependencies was measured to be negative 2.3122. The magnetic dipole moment was 8.398 amperes meters squared. So experiment assumptions. I just assumed that the only magnetic force that acted on the magnometer was from the bar magnet. So the first part of this was to find the magnetometer sensor by sliding the phone across the east-west axis to find the minimum and maximum x values, and then next we slide the phone across the x-axis to find the magnitude of the magnetic field of x values. So for 20, 70, 120, 170, and 220, this is done 3 times and then averaged. And then after finding where the y component is 0, x component is 0, you find a distance d perp, which is the perpendicular distance, where the net magnitude is 100, and then record the x, y, and z components at this location. And then you repeat this 3 times and then record the distance and the net magnitude. And the surroundings in this case are the ruler, phone, earth, while the system is the bar magnet. So I observed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So here are what the results look like, and you can see for each run it's all averaged. And then our equation is negative 2.3122, and then the constant is negative 3.297. And so when we compare the equation on the graph, we can find the distance dependence n, which can be found by first taking the distance dependence equation, taking the natural log of both sides, and then ln k should be the same as the slope, so that your distance dependence is negative 2.3122. And then in order to find the magnetic dipole moment, you take the constant, which is negative 13.297, and substitute it into e to the ln k, and so you get 1.6975 10 to the negative 6. After rearranging the last third equation, you get 1.6795 10 to the negative 6 divided by 2 to the 7th power, and then you get 8.398 ampere meters squared, as you saw in the results. So possible errors are that the other magnetic forces acting on the magnetometer, such as other electronic devices within the area, inaccurate locations found for the magnetometer sensor causing slightly off results, and then finally the meter stick could have been slightly tilted or moved due to sliding the smartphone, causing the XYZ values to be off. So for coding, first we created a function for the magnetic field, and you can kind of see here that is the Biot-Savart law. And then next we visualize the magnetic field. Then we set the different observation locations and use the dipole functions for the on-axis and perpendicular axis locations. And then we average the d perp from the experiment, and then observe the locations at 45 degrees from the axis. And the idea behind the model is to calculate the magnitude of the magnetic field for on and off perpendicular to the magnet. Finally, getting results, we have a distance of 0.302642, and then b at 45 degrees at distance d is negative 4.94 10 to the negative 4 and 4.54 10 to the negative 5. And using this model, I found the magnitude of the net magnetic field was 4.9636 to the negative 4. This is in contrast to the experiment result of 3.1462 10 to the negative 5. So finally, if you you oriented your setup to compensate for magnetic north. If you hadn't done that, the effect of the Earth's magnetic field would have been measured with both the Earth's magnetic field and the bar's magnetic field, and this would cause the value to be significantly higher and inaccurate. And if you had two identical magnets, what would have happened? The magnitude of the magnetic field would have been twice as strong as the magnetic dipole moment, and however, the direction of the magnetic field would still remain the same.